Third day, morning section of the third day. First talk will be by Uri Ascher. I guess he's going to speak in English, not Portuguese, right?
English.
Okay, he's going to speak in English. He just confirmed. The title is Numerical Analysis in Visual Computing, What You Can Learn from Each Other. So, thank you.
Thank you. I found out that I can give talks only in English, even though I speak 3 languages more or less, 2.5, but still. When it comes to talks, only in English. So I know that this is different from all the other talks in this workshop, but you know, something else in the morning. And I'd like to talk about a community called visual computing. I don't know if you ever heard of this term, but there are actually various big labs and departments called visual computing around the world. And for me, it's a combination of computer graphics and image processing. Okay, from the point of view of numerical computation, the main difference between that community and other communities is that you're not trying to produce in your algorithm some result that it is accurate up to a tolerance epsilon or something like that. What works, what is acceptable as a good result is if it looks good. And so, for example, if you think of your living room and there's a carpet in your living room and you step on the carpet somehow and suddenly there's a wrinkle on the carpet. And so the error is how high it is above the floor, yeah? So the L1 error, it can be very, very small, and yet you see right away that there is a wrinkle in the carpet, you know, and vice versa. I mean, if you can simulate that, maybe the error everywhere is not so important. So it's different ways for appreciating the results that you get, and that leads sometimes to different algorithms for computing. By the way, I do scientific computing. This is my area. And so this is the motivation of this talk, if you wish. And I want to show you 2 case studies examining the relationship, if you wish, between these 2 communities of numerical analysts / applied mathematicians on one hand, and people who do visual computing on the other hand. In the first case study, I would like to suggest that this community is getting closer to the numerical community, in a sense. In the second study, I would like to suggest that this community may need to get closer to that community because they are ahead of us. Okay. So the first case study is about a simulation of a deformable body. Okay, so this is not a deformable body. And as massive and terrible it looks like, it has only 6 degrees of freedom if it moves. But my shirt, for example, I have a shirt here for you. The motion of this thing, if you think about it as a mesh with springs, a mass spring system describing this, that will be many degrees of freedom. Okay? Likewise, the pillow in your hotel room or at home. If you lay your head on the pillow or sit on the sofa, you know, there's a deformation there which is way more than 6 degrees of freedom, obviously. So it's harder, in fact, to do it. My collaborators in different projects here are Edwin Chen. Oops. Yeah. Edwin Chen is a PhD student jointly with me and Dinesh Pai, who is a colleague of mine. Danny is in Adobe, and Dave is in Toronto, and Bing Wang is a young faculty member in Beijing, and Hui Huang is an ex-student of mine who is now a big chief of a huge visual computing lab in Shenzhen, China. Okay. So it's not only in computer graphics, also robotics. You need soft touch in robotics, so you have a similar kind of soft body interaction. And it turns out that high-quality simulations can be very expensive. There's a huge literature on this. And sometimes you need to calibrate the model. That leads to inverse problems. How to calibrate the model. And basically what you have is, oops, not so fast. You have elastodynamics equations, and you need to simulate those equations either in the forward sense or in order to find parameters. You may want to actually not only display results, but also to control the motion or to even fabricate it. 3D printing is a big thing nowadays, second only to machine learning. And so there are quite a few problems here and quite a few different approaches. The approaches depend on the goal that you want to achieve. Okay, so what you have really underlying the whole thing, you can think about it as a system of pretty disgusting looking partial differential equations in 3 dimensions, space dimensions and time. But typically people look at it at the variational form and already apply finite element method. There are codes for that. Then what you get is a moving tetrahedral mesh and a bunch of ugly ODEs looking at it. So for example here, you have a plant, and the plant is described by a fine surface mesh, but in order to simulate this in 3D, you need a tetrahedral mesh in 3 dimensions. This is the domain, okay? And there is actually some software that allows you to move from the fine surface mesh to a coarse volumetric mesh, and it is this volumetric mesh that you simulate as the plant moves. The plant moves because there's water or wind or something like that affecting it. Okay. So to obtain, so there are parameters in the differential equation, namely Poisson ratio that we will ignore, but what we will not ignore is Young's modulus. And you want to find those parameters because to allow a simulation that is better matches observed results. And so there's an inverse problem to solve. For that, what we do, there's the plant. And it's surrounded by Kinetic machines, and they take, so you tweak the plant, okay, so the plant then moves in the controlled way, and then you get point clouds, a series of point clouds in time, okay, and from those you want, by simulating those differential equations, you want to do motion tracking. And then from that, you get, by a process that I will not now discuss, you obtain values for the Young modulus. So as I said, this can be a pretty enormous problem, and also there are different purposes. One purpose is that once you calibrate, all you do is simulate, produce beautiful simulations. I can show you this if I have time. An example of that, maybe not. But maybe you, as I said, you want to do something more like a control of it and so on. Then you may need different kind of results, different quality results. Here are the equations that we are faced with, having already discretized using a finite element method on the tetrahedra. And so this is a mass matrix times, so the Q's are the nodes of the tetrahedral mesh. Yeah? And so you have that masses times accelerations is equal to forces. And the forces are elastic forces, damping forces, and external forces, such as gravity. And the elastic forces here are the gradient of the elastic energy, potential energy. Okay. And in the simplest case, that would be just quadratic, and then the force here would be linear. And that is relatively simple, but there are situations, for example, new Hookean laws, where the energy here is not only not quadratic, but it can be non-convex as well. And the damping looks like some matrix D that depends on Q and V times, on Q rather, times the velocities V. V would be the velocities, Q would be positions of those nodes.
For each point.
Yeah, for each point of the tetrahedral mesh. No, a nodal element method. So this is a typical thing to do. There are two things here. One here. One is to write it as a first-order system for the positions and velocities. Okay, and the other is to pick out the leading term. This matrix K is the stiffness matrix, which, I want to say tangent stiffness matrix at a given Q. Okay. So this would be constant if the energy was quadratic, but it will be uglier if it is not. And the rest is here. You just write this term because this is supposed to have the major terms of the right-hand side of the total forces, and the rest is G. Okay. So as I said, it can be planned, and that will be a finite element method. This here, cloth, usually the model is a mass spring model for this different model, and it corresponds to the eigenvalues that you have being either very large or very small, but not a complete spectrum, as it would be for the finite element method. Now, if you look at this thing moving, okay, this deformable body moving, and if I try to stretch it, if I stretch it, especially if it is a stiff jacket rather than this very stretchable thing, the stretching could be very difficult. In other words, it can be very stiff. You can have large eigenvalues in the stiffness matrix. But when I make it move like this, you don't see high oscillations. It's one of the things in computer graphics. You have high oscillations to take care of in sound, but not in vision. You just don't see high oscillations. Okay, so it is possible to say I want a step size in the discretization that will be commensurate with the motion rather than with these high oscillations that I do not see. I do not see them because there's damping. Okay. So we want a step size tau, which is commensurate with a damped motion. And this is a typical situation for stiff equations, if you know what it is, where you want a large step compared to the scale of the problem, the highest scale of the problem. I should say the highest frequency scale. But here it is highly oscillatory rather than damping. Yeah. Can't use explicit methods because of stability of the numerical method. And so you want implicit, but now for implicit methods, you have to solve a system of nonlinear equations. If you're still with me on this, you have to solve a system of nonlinear equations, and that can be a nasty system of nonlinear equations. Because you have all these oscillations, you have a lot of motion in one step. And so you cannot just say, oh, it is pretty close to where I am. The next one, I can have a very good initial guess for it, and so on. You cannot assume that because you're taking a large step. So what Baraf and Witkin did in '98 is to break loose from all these people who do geometric integration and say, let's use backward Euler, which is a horrendous thought for people who do geometric integration. And they said, the whole thing is damped, and therefore we are going to use backward Euler to damp it. Moreover, backward Euler also requires solving nonlinear equations, therefore we will just do 1 Newton iteration per step and continue. And that is called semi-implicit. They didn't know that. But this is called a semi-implicit method. It is existing in the numerical literature since, I think, the 1960s or something. Anyway, this was actually a major step in the computer graphics community life. And then this, in fact, to date, it is still a very popular method, this kind of basic thing. But here comes the numerical people and say, come on, there's a lot of heavy damping involved here. Moreover, this is not the damping like here, which is physical damping. It is damping that has to do with the step size that you took. Okay, so how are you going to think of some artist in Walt Disney studios? How is the artist going to be told what kind of step size to take? Yeah. So And also, why does it work at all? If it has huge error, why does it work? Why does it look? I mean, it works because people have been using it for 25 years. It must work. Yeah. So you have these kind of methods with high damping. You have, on the contrary, conservative methods, symplectic, if you don't have damping, like implicit midpoint or explicit leapfrog or energy conserving. All these methods don't have any damping. And any artificial damping, I should say. And then you can mix them by theta methods and generalized alpha. That's the method that people are using in Disney nowadays. You can also do exponential differencing. I will mention that again. The nice thing about that is, like the semi-implicit, you don't need to solve nonlinear equations at each step. And then you can try to decouple fast and slow scales. I know how to do that for very simple problems, but not for more than simple problems. So just to remind people what these methods are, if I look at a system of ODEs, the derivative of u is equal to b of u, the time derivative, and I want to step from t sub n to t sub n plus 1, step size tau, okay, then backward Euler is just the next solution, next step solution minus the current one is over tau, over the step size, is equal to b sampled at the unknown un plus 1, whereas midpoint is same thing but sampled in the middle. It makes a big difference in the behavior of the method. And then this one here, both of them actually have the unknown here, so it's a nonlinear system to solve at each n. And so if you do it by 1 Newton method, then this is SI. Okay. I want to show you those methods in action in a moment. And then here's work quite recent, in fact, got accepted. The paper got accepted, I think, when I was already in Rio. And what we looked at is to write over a step. You write the differential equation in an integral form, and then you freeze u here, and so on. Everything is frozen except for the exponent, and so you can integrate this exactly. This is called the Euler kind of approximation, and you get this sort of system. It doesn't matter exactly what's written here. What matters is that you need to, at each step, to evaluate the action of the exponential matrix times some corresponding vector.
Who's J?
J is the Jacobian of B with respect to U. So the solution of nonlinear systems has been replaced by a matrix vector multiplication, but with the exponential matrix. I mean, you don't want to form this matrix. It will always be full. And if it is 150,000, it's going to be 150,000 by 150,000. You don't want that matrix. You only want the effect of that over on a vector. I want to show you a little, the question is, why are you doing this? Yeah? So let me show you a little. Maybe we're not going to see it. It's annoying, actually. I want to show you something else instead. you can get results of this sort by this dumb backward Euler kind of method. So I just wanted to convince you this is not nonsense. In fact, it actually produces some results. Yeah. Let me see. So this is effect of wind and so direction as well as magnitude. Heavy rendering. We even did some validation. I'm not going to go through this. To actual validation, quantitative. Well, this is small steps that were taken there, but still. Unless you have high vibration, the validation is pretty good, and it is way more than mathematicians usually do. It's actually measured against the thing moving in reality. Anyway, I don't want to go into that. I wanted to show you another movie which for some reason refuses to show up. It's not my day. Anyway, so this is the last frame really of the video that I wanted to show and refuses to show. But the point I wanted to make is, so this is a backward Euler. You twist the bar. Yeah? And this is the last frame of the backward Euler, semi-implicit, midpoint, and this exponential method. And the point is that backward Euler, even though it's obviously, this is as close to true as possible, if you wish. And you can see that this is totally wrong point-wise. Nonetheless, you see the twist, okay? It's like damped energy must the same motion. That is the important point here. And that's why this, even this one is like that. You can see the twist, but it is with less energy than it should be. So, of course, an artist will say, okay, well, I'm going to run the movie faster or something to get the right effect. The point is, it's not nonsense. The error is not nonsense. It's an important thing to understand, even though it's order 1. Okay. The nice thing about this exponential method is that it is almost as energetic as implicit midpoint, which is a conservative method, so there's no loss of energy. Okay. And yet, you don't have to solve those nasty nonlinear equations. In that video that I cannot show, why? Actually, I tried it in my office here only a few minutes ago. It worked. Anyway, the thing is that, the method that do not require the nonlinear equation solution can be faster by a factor of 5 or 7 or something like that, just because of this fact. There's another one that I will not show. However, here's a paper of people who say, well, I want to have a gizmo here. I'm going to flip it, and it's supposed to cross and land correctly on the other side of this barrier.
Could you enlarge it? It's going well.
This one? Oh, yes, thank you. Thank you. Forgot myself. So now you need to control it. You cannot do anymore this check with the backward Euler. You need a method that would be a bit more closer to reality. Because otherwise, how can you control the motion? The same people here, I have a little video that they produced where they have a walking table. They have a table with flexible feet, and they put it on a kind of downhill. And now you want to design it such that it will run the fastest. Okay, I'm not going to show it because I'm being taped, and this is not my work. I'm not going to show it a video that is not mine while I'm being taped. So, but believe me, or come to me over a coffee break. I'll show it to you. Okay, so what's going on? You can actually do some simple analysis. You can take just one equation, one Q, not 150,000 of them, just one. And so second derivative here, plus the damping matrix becomes just a factor d, a constant, times velocities, plus the matrix K became just omega square 1 frequency squared times Q. And now the damping here is going to introduce damping. Yeah? And so you can calculate just the damping, not the exact value of the solution. You can calculate that. And now, next we are going to set d equals 0. And if the method introduces damping, then we are going to try to relate what the method does to a solution of this equation in terms of damping. And so that's going to give us damping of the method, d method. Okay. So here is an example for backward-Euler. It's the same as SI, as semi-implicit for a trivial linear equation. So the damping of Euler over omega as a function of step size tau times omega. So this is step size times the numerical method, step size times the frequency of the differential equation. It is not going down or up linearly or monotonically. It actually has a max over here when tau and omega, time times omega is 2 or something, order 1. Okay? When omega is increasing as tau is fixed, so we're here, nicely, it is decreasing, but not too fast. Okay? And so that's why if we damp a bunch of high frequencies, it's still okay because they don't change so fast from one to another. The action is relatively boring in the high frequency range. And so people from computer graphics looked at methods where the D method is 0. And in fact, these guys that I mentioned who wanted to control the table running down use this method which is symplectic and conserves momentum when D is 0, which is the case where you don't have damping. Okay. This method is by these very good mathematicians such as Marsden. And so suddenly that community that was kind of, I don't want to say primitive, because as I said, in some senses they are ahead of us actually. Well ahead of us, I should say. But in other sense, they were primitive. And here they are, using Marsden work. Yeah. So you see, I mean, they were going in our direction. They are going in our direction still. And again, I've been writing sporadically papers for about at least more than 15 years now in this community, and believe me, the attitudes of that community has changed. So that they appreciate more what people in numerical computing do. This is a ball hitting a sheet, okay? And so again, implicit midpoint is most energetic. This one here, so this is collision. This one here is the exponential method that we are promoting. And the flat guys are the backward Euler and the semi-implicit method. So there's a ball hitting the sheet. And you can just draw the energy and you get the effect that you expect. Okay? So a big loss of energy in the semi-implicit and backward Euler, and little loss of energy for this exponential method. This. So you may say, why don't you just forget about this backward Euler semi-implicit? We can live without it so well. So here comes something that not every numerical analyst knows, and that is that in fact, even if you have energy conservation and therefore your method is stable, that doesn't mean that the solution is meaningful. If you take a large step, it can be nonsense, stable but nonsense at the same time. Accuracy does not follow from stability. Okay. So also exponential methods lose charm. So when you have something really stiff like a Harley-Davidson jacket, I don't know if anybody here is into that, kind of very hard to stretch. Then you don't want to forget those methods because those are the only ones you have, in fact. Okay, they produce results which are not correct, but at least look like something damped, as opposed to these methods that are it's hard to solve for each step, and it's not clear what you get when you're done with that. So what can we do? Well, we can do mixing methods. I will mention that in a moment. And as I said, this one I will not talk about at all. If you do molecular dynamics, nobody knows how to do it as of yet, after I don't know how many decades of work. So yeah, you can actually get into really difficult problems here. So just to mention that you can try to control the amount of artificial diffusion by taking something like implicit midpoint that has none of that, and backward Euler. This is the DBF2, second order like backward Euler method, and mix them with the factor theta. And if theta is 1, then it is just the diffusing method, whereas if theta is 0, it's the implicit midpoint, so you mix them. And you get something like this. The higher the theta, the more diffusion or damping. And generalized alpha, a method that engineers love for reasons that I still have to understand. You get something similar. Not quite the same, but similar. So the point that I'm trying to make is that from qualitative, there's a movement in that community from qualitative to quantitative. Now I said it. And that brings them closer to mathematicians and numerical analysts. Any questions on this before I move to the other case study?
When you consider, you are considering linear damping, I was feeling curious actually if there is, when you have quadratic or higher orders of, for the damping term with velocity, would it have a rule? What would be the speed that would change the necessity to go from linear to non-linear damping effects?
Oh, I did not talk about actual damping at all. Let me say just 2 words because it's actually a complicated subject. So the truth is that nobody really knows how to model damping correctly. People use Rayleigh damping a lot, but this is suspiciously good for theory. So you think that it's there because you can actually do theory. You can actually find the eigenvalues and eigenvectors with this. But more generally, people have shown that there are damping situations where that will not work. That will not explain what you see. And then the general question of damping is an open problem, in fact. Yeah. What I was showing was one example in order to see in the simplest way the essence of what's going on. That is all. Image and surface processing, I think that I'm getting now further away from what most people are looking at here, but still. Nonetheless, I have the feeling that everyone must have seen this picture. Somehow, people, they've been working on our brains with this picture. The camera, it has a name, the cameraman, and it is noisy here for some reason that I've never figured out why is it noisy. Nonetheless, and you want to remove the noise, but not the features. Okay, that's the essence of denoising here in this case. You can do the same thing. You can look at the same problem, but this time it is a rendered triangle mesh, just like for the plant, a triangle mesh for a body in 3 dimensions. So it's a surface mesh. And you want to remove the noise to obtain Igea, the famous, beautiful statue. I think it's Greek statue from a long time ago. Okay. Oh, but you can talk about denoising, but also deblurring. Okay, that's a much more serious problem actually. That it is in constant interest. In painting, you want to remove the wires from your picture. Completion, image completion, which is you're missing more serious part of the image. Silent features, finding silent features, and so on. Many interesting problems there. Image processing is very popular nowadays, of course. And I would like to now introduce what I will call the paradigm, a popular paradigm okay, which uses a diffusion or anisotropic diffusion as a regularizer. Okay, so you have F. F would be the denoising would be identity, but maybe it's deblurring or something operator operating on U, where U is the image, and you have data. So the image that you have is B, and you want to find U such that the operator on U will not be too far away from the data, plus a coefficient beta times R of U. R of U is the regularization or prior. People now call it prior. I think it's better to call it prior of what you expect it to be. And this R of U is often the integral over the domain of the image of either you have here the magnitude of the gradient of U, and it's either to the power 2, where it will be least squares, or to the power 1, where it will be total variation. Okay? In case of total variation, you actually will have a problem when it hits 0, and so there are fixes, and in fact, we worked in 2006 on using a Huber switching between the power 1 and the power 2 here. This is big things. There are lots of papers on this stuff, even though it looks trivial here. Huge amount of work followed. There's a bunch of books on this stuff, as well as I don't know how many, I think it's thousands of papers. Perron and Malik had an original paper in 1990, Rudin, Osher, and Pertame 91, a famous paper. There's a book by Weikert on multi-scale kind of approaches. There's a book by Chan and I forget who, Chan and many paper by Chan. We also were there. And these are papers from computer graphics that all, in some sense, use this sort of paradigm. Okay. Now comes the question I would like to ask, does it make sense to use this paradigm? No. I would like to ask, does it always make sense to use the paradigm? Okay. And in the community of numerical analysts, this is a heresy to ask this question, because everybody uses it. They've been using it for 27 years now, since 1990. How can it be wrong? So of course we use it. If you talk about some top people in computer graphics, and I've done that, then they will say, why do you ever want to use this? So there is a variation of opinions here, dichotomy, I would say, of opinions here between the two communities that I'm trying to sort of relate to one another. So not everybody likes it. And the question is, why? Okay. I should say that, the social and psychological aspects of this thing are more interesting, in my opinion, than the actual thing, because there's a community led, by the way, by in my opinion, the best numerical analysts, period. You know, so it's not something, you know, in the back mind or, no, these are the best people. In a trench, I mean, I had this view of a trench from the First World War. And, you know, people are in the trench, and so long as they're in the trench, it's okay. You know, you can prove theorems to each other. But when you really want to improve your numerical, your image results, from the point of view of images, you have to move out of the trench, and now it becomes dangerous. Yeah? You can prove much less, but so I want to explain, so my contribution of now is just to try to explain what is it, the source, okay? But the observation that in general, these two communities diverge here, I mean, this has been known to me at least from the beginning of the century. It's not new at all. Okay. So here are these two things, you know, just to collect enemies here. You have an image, so an image in Rm by n, okay? And now you do something to it, and the result is in Rm by n. Why is it obvious that you have to go to some Banach space, or rather Sobolev space, change the Sobolev space, and come back to the same discrete space? It's not the same as Navier-Stokes, where you start with some molecular description, you go to the differential limit, if you wish, and now you do discretization that has nothing to do with the molecular level. Yeah, but here it's the same guy at the beginning and at the end. It's not obvious that you need the PDE. It's not the same thing. I'm not saying not to do that, by the way. I'm doing it all the time myself, and it will, you know, it will be cheating of me to say don't do it when I'm doing it myself. But I'm saying that you need to justify it. Okay. Second one is worse. This is actually global. This is global integral over the image. So you have somebody special. I want to take a picture of that special person. We go out, I'll take the picture of the person. And so there is, in the picture, there's the person, and then there's green around here. Yeah. Now I want to process it. The green weighs exactly the same as the person, you know, per square centimeter of the image. That's not how Photoshop works. It's all local there. It's not a global thing. So where this matters is where the communities differ. Of course, there's a reason why people have done it. And again, these are top people, really top, the top people I know. I've done it for 27 years. Yeah? You can obtain more theoretical backing. And I'm not just talking about proving more theorems. You actually have some theoretical foundations to what you're doing. The algorithms that sometimes appear in image processing, if you try, I mean, I do this, and then I do that, and then I do this again because I have to fix something, and then I do you wonder if that will work for you too. You know, if, the theoretical foundations are good. However, the disadvantage is that it may be outperformed. I mean, the actual foundations may lead you to use methods that are less than great if the forward operator F is simple and the data is of high quality. If the data is of low quality, then you don't have anything to fix. You know, it's okay. If F of U is complicated, then likewise. Okay? But if F is simple and the data is of high quality, then there is an issue. So when is it worthwhile to use the paradigm? If the forward F of U itself contains differential terms, of course. Okay? So if what you're doing is, I don't know, EIT or Maxwell's equations, I've worked a lot on that at one time. Of course, you're going to use also a regularization operator which includes differential terms. It goes without saying. However, if that's not the case, then still you can use it if F of U, for example, is blind, not just deconvolution, but blind deconvolution. Okay, and these guys looked at the time of flight data, so the data are not high quality, and they wrote some very nice papers, in fact. There are additional uses in computer graphics for this sort of idea, sort of paradigm. But I want to now show you examples where this is not always the case. The examples are of my own work, but from a long time ago. The point is not to describe what I did, but rather, this is where I know what went on in what was under the hood. Yeah, what went on in the kitchen. And so this is why I want to tell you about it. Yeah. So so this is the denoising of triangle meshes. Why do you want to do that? That's a question that is hard to answer, so I will not answer it. But let's assume we want to do that. Okay, and so here is a bunny, the Stanford bunny. And here it is noisy. So this is actually the bunny, and this is noisy, a noisy version of the bunny. You want to remove the noise, but you want to remove the noise without removing the fur. Okay, so there's a texture here you don't want to lose, and that's the result which does the right thing. But if you're not careful, you're going to get a smooth bunny, and that's not what you want. So in particular, there were two papers by Tadmor and a bunch of people in Ascher and other bunch, where they use a multi-scale iterative refinement that I really got hooked on that idea at the time, where basically they use a theorem that decouples bound BV space. And basically you have a bunch of layers of frequencies, if you wish, and you add them one at a time, okay, until you hit all of the texture is recovered in the space that you're growing in this way. But when you do it for the bunny, that's a different story. And in particular, what does it mean to denoise a triangle mesh? You have nodes, Q, we called them before, and each one of them is three XYZ components, and it means position as well. So what is it noisy? It's just not just value. It's not just intensity like in image. It's actually a position that it is noisy. So, so really the best thing to do is to denoise in the normal direction. So you find the normal direction, let's say here at the back of the bunny, you find the normal direction and you denoise in the normal direction, not in the tangent space, but in the normal direction. Okay. But now if you do that, then how do you find the normal direction? To find the normal direction, you're looking at the closed neighborhood here. That's how you're going to find the normal direction. You're not going to look at the feet. The normal direction there has nothing to do with what you want. So it's local, it's not global anymore. Okay, so if you're going to use a Laplace-Beltrami there, you're not going to be good. People did that. So what we do is we look at a neighborhood of a particular edge I, and then Qi is updated by something called delta Qi times the step size plus some fidelity to the data. And this delta Qi is such that the result of the change of the denoising is a scalar times the normal in the direction, and we found the normal looking at the first neighborhood of that particular node. Okay, what goes in here doesn't matter. I mean, it's a simple computation. That's the point for us. But the point is that it works very well if you don't have too much texture, and it's as fast as it can be imagined, because you have to visit each node. Each node has a fixed number of operations, not very large. It's optimally, the complexity of the algorithm is optimal. No PDEs. You're not going to be able to solve Laplace-Beltrami in a linear time so easily. Yeah? So it is much faster than differential topology sort of algorithms. And now for the texture, what we do is we gradually reduce the denoising effect and add more fidelity to the original data. There's, of course, this question of where to stop this thing before you stop fitting, maybe eventually you're going to just get the original data with the noise. So you have to do it, but all of the algorithms here are similar in this respect. And here's the result that you get out of this. So this is 135,000 vertices. It's not small, okay? And that's the given thing, and that's our result. And you can see the details of the eye here, of this thing here, and the curls, which you do not see in another method. And it takes 13 seconds on a computer from 12 years ago, kind of a garden variety computer. Okay. It's very fast. Can't get that if you introduce yourself a PDE in there. Here's another one, a bit more recent vintage, but still quite a long time ago. You have a picture of pieces of a dish, and you want to put it together. So, there's a registration problem here, obviously. You want to put these pieces together. But this is a TELE-REGISTRATION because these pieces are not close. If you have done registration in imaging, you would know that the registration is usually very, very small change. Here the change is not so small. So what we do is we look at the salient features. For example, we look at this piece here, and there's a salient feature here that hits the boundary. Okay, this one has this, and so by finding the salient feature, we connect them And that's how the registration is done.
Nothing's missing. Nothing's missing in this plate. Nothing is missing in the plate.
Actually, there is a piece missing here.
Okay.
Yeah. You have to. Yes. Ah, come on, this is not perfect. Okay, if it were perfect, it would be fake. This is the result of the algorithm, I should add. Yeah. So that's what we do. First of all, we do the salient features, okay? Actually, here too, you want to find the salient features like this one we don't care about because it doesn't go to the boundary, so it doesn't match anything else. But the ones who do, okay? You find the salient features, you match them, and then you do, there's a completion, image completion here. I'm not getting to that. And then in painting. Okay. This is how you get that. And this is the description of the algorithm. Here's another one. So we want this plant here is in the way. Okay. So the user says erase that. Okay. This is erase that. So of course, this creates a hole here. And so what we did in this case was to take a piece from the leg and insert it here. And now again, the salient curves say how you insert it. So what you see here came from here. Yeah. This requires a lot of hand-holding. Let me not cheat you here. But you've got to admit that this looks better than the images that you see in biophysics imaging, right? So there's a quality here which is different from the one that...
you put these two white strips there, but you could put basically everything. So no to Trump. I mean, you just invented what's there.
It's a choice. It's a choice. I mean, so you have the user actually uses a system and makes such decisions, yeah. Including, as I said, deciding which part here to be removed. Yeah. I want to show this example because it is closest to my heart. It was taken by my wife, Nurit, and this picture here from some place in Cambodia in the jungles, and it's an archaeological park there. That we were alone in the archaeological park. It was kind of far away. This is a wall, and with the years, 900 years, the blocks moved, and so the relief sort of here, you can see it doesn't fit, and here there's a person here discombobulated. Yeah? So what you want to do is, first of all, move the blocks, and then in paint. And so here now, this is the result of the efforts. You can see that this is much better. When we wrote the paper, this actually started the work for me, to try to fix something like that, okay? But when we wrote the paper, my colleagues, who are real computer graphics people, unlike me, said, we don't want to put this in the paper because it doesn't look impressive enough for people from that community. You know, so it exists in the project page of the paper, but not in the paper itself. So I said, come on, guys. I mean, this is invented. The whole thing is invented. This one is real. And they said, okay, we'll put an example from Egypt, because in Egypt, a similar thing is 3,500 years old, not only 900, and therefore the changes are bigger, so you can see a better improvement. And I said, come on, who hasn't seen the picture from Egypt? This one is unique. But this did not go through. This sort of argument was too much. Anyway, the other thing I was going to say is that the computer, the camera that Nurit uses has about 32 megapixels. Again, are you sure you want to solve a PDE with this many pixels? You know, you have a matrix there, a huge matrix there to deal with this sort of resolution. Okay. So this has to be done as a last resort, not as a first resort. So incorporating mathematically sound techniques into methods and algorithms for computer graphics and image processing is becoming more popular. You can write a paper that sounds a bit more like what we are used to read, and they will read it, which is not true 20 years ago. There are significant advantages gained in this way, and you can actually sometimes use math in order to get a solid idea of what you're doing. Okay, that's important. That has always been very important for me in this area, and bridge the gap between qualitative and quantitative. But you don't want to just be hooked by the mathematical prowess and never mind everything else. There's a reason why we do that. We should not forget the reason. And there are situations where the physics and the physics-based simulation, the gap is too wide. That made us change the methods. Okay? And yeah, as I said, you don't want to get stuck with on the idea of proving theorems on total variation, for example, and Bregman distances and things like that, and forget what we came here for. Yeah, it's important to remember. Thank you.
Questions?